right, so we're starting the sensor session led by Jascha. So floor is yours.
Let's see here. Can I join from my desktop as well?
You should be able to. You'll have to let yourself in.
Okay, so I can open it. Very good.
You may want to make your desktop sign in the host so you can share from there. But yeah, if you
can I not share my screen?
All right, then let's just talk.
Well, there we go.
There we
So,
go.
can you see my screen?
Yes.
Okay, perfect. This is very often kind of how I have a lot of meetings during the day anyway, is just effectively live Googling and drawing things and slides and whatnot. So we can kind of hit that. So yeah, I think so. The first kind of thing, let's do some definitions. So I think so everybody's kind of here is like familiar with the notion of what a sensor and a sensor is. I think let me just give my definition to see if we're all on the same page. A sensor to me is a form of transducer. Now, I did give a motor talk a while ago, and a motor is also a transducer, but the key differentiation for me between an actuator and a sensor is simply that the energy flows one directional. So usually when we're going from one form of energy to another and doing that conversion, it's often one directional in the case of a sensor and bidirectional in the case of an actuator. That's kind of the working definition that I have, and kind of lets me think about, because there are some things that go both ways in edge cases, but that's my basic working definition. I think the second key working definition here is the notion of a passive versus an active sensor. And let's see here. For that, the definition I work with is an active sensor is a sensor that converts energy that it sources. So this is simply that passive sensor is gathering energy from the environment and converting it into another form of energy. And an active sensor is then providing that energy that it then receives. In some cases, as I mentioned, because we're talking about sensor versus actuator, some of these sensors will actually use the transducer to both create that energy and put it into the environment and bring it back. I think the most classic example is just be the sonar, right? In many cases, you'll see kind of an emitter and a receiver pair, but there are many of these, especially in automotive, where you'll actually see a single transceiver where this transceiver, it hits the air, creates the pressure wave, it starts the clock, and then that same transducer actually receives the signal as well. So this is, like in this particular sensor, this is where we have a dead time is one thing you'll encounter with an active sensor, where if it's using the same thing to sense and receive, there is a timeout when it's kind of like ringing down and getting prepared to listen as opposed to make the sound or the light or whatever it is. So that's really it. Sensor versus actuator, talked about that. And then active versus passive sensors, talked about that as well. Does that kind of make sense to everybody? Does that check out with everybody as a solid working basis?
Yeah, I'll just ask, what's the definition of what is the definition of a transducer? Like, you sort of started with that, but I'm like, well, I don't really know what that means.
Transducer is an element that performs transduction of energy from one form to another. So like an electric motor goes from mechanical to electrical energy. And in my earlier talk, I said there's an intermediary step where we convert it into magnetic potential energy and then back out. So there's like an intermediary step, but in terms of just the black box that's doing the transduction, it's one form of energy to another. just to kind of get right into it, like a camera is going from light energy photons in the usually it's the visual spectrum, that's what we're usually talking about, into electrons. And I think it goes without saying that most of the sensors that we're interested in, the output like energy form is electricity, since that's what we can plug into our sand that thinks. And we need to be able to have all of these different physical world quantities converted into electrical energy that we can then do computation on. Does that make sense?
Yes.
Is that fair?
Perfect.
It's interesting that you started with kind of the physics transformation. Like when you said, what's your definition of a sensor? I think my mind first went to, it's a transfer function that you can sort of invert easily so that you can put it in series with the world, and you can sort of do a deconvolution and sort of eliminate the characteristics of the sensor device so that you're getting clean information passed through from the world to some sort of processing unit. So I'm trying to make a distinction between what's the essential difference between an actuator and a sensor. And an actuator, I think of it as it's trying to act on the world, so it kind of makes its presence felt, whereas a sensor ideally is something that vanishes. So you might, for example, have one that's very high bandwidth relative to the sort of spectrum of the phenomena being controlled and so forth. So I think this is kind of a control engineering bias. I start with control theory math definition of a transfer function as the starting point. Transfer functions and convolutions, that's kind of what come to mind for me.
Yeah, that's very interesting. And that's the other question I wanted to speak to was thinking about sensors as a question answering device. And very often the sensor output alone is inadequate information to directly answer the question. And the question can only be answered with computation. So in that sense, this is where we start talking about a sensor which actually has to perform inference on some raw data. Like the parsed data is actually what you're interested in, and the raw data has some kind of an energy penalty associated with it. And this also gets into the notion of sensors eating sensors, where we have some sensors that are very inconvenient, costly, not robust, or what have you, but they directly answer the question with a simple, let's say, digital pulse. Like for instance, maybe a good example would be the problem, the very common problem of people counting. People counting sounds like a relatively trivial thing to do, but it turns out it gets to be pretty complex. And maybe one example of, actually, I'll back that out. An even better example, trying to measure the mass of something. The easiest way to do that is simply to put it on a scale. That's often not feasible. So instead, we could indirectly measure that using some other modality, like maybe the example there is, what was that kind of like bank robbery movie where they measured the deflection on the suspension springs of the truck. So they were actually using some other element of the system combined with computation to actually get a measurement, which is a very roundabout way of doing it, instead of just actually having the sensor there, which in that case is impossible. And it also just this is just, I think, something we should also keep in mind. If like a sensor is answering a question usually.
So not to derail the discussion right at that sort of premise point, but I think there's actually a very interesting philosophical question right there. Like if you draw a boundary between processing to answer questions versus sensing to just create raw data streams, you can make that like a thin sensor, fat processor, or a thick sensor, thin processor kind of question. But there's also this question of like how do you sort of sense the environment in a way where you have the information you might need to answer any question, as in you don't know the question that might be asked, but you kind of want to have enough coverage. And this is, I think, what this is like in controls, that would be the observability analysis. Like you have a state to model the whole thing, and is the state observable is the kind of question. And now distributed computing people talk a lot about observability as well. And I'm trying to think of like a canonical example of that to me is proprioception. So in the body, you've got like 5+1 senses, right? And 5 of the senses behave like the way you're talking about. Like the eyes, they see, but they're also controlled. You look in a particular direction and then you see over there. With ears, it's less so. There's a fixed frequency range and you can't easily find the direction, but still to some extent, you can kind of like, cup a hand behind your ear to like direct what you're paying attention to. Taste is definitely sort of directed sense organ. Smell is more of an observability thing. If there's a smell in the environment, it'll get to you, right? So even the top 5 senses, they kind of like range from extremely active and sort of directable like eyes, because you have eyelids and controllable gaze, to ears, which are somewhere in the middle. And I think smell would be the least controlled. It's just environmental presence. And then proprioception it's completely out of your control. You kind of just sense your body, and if your leg gets amputated, you have like phantom limb syndrome and that kind of thing. So that's at the other extreme of observability without clear ideas of what you're observing for. So I would sort of, I guess I'm drawing a distinction here between, you've made several distinctions, passive versus active, and I forgot what the other one you mentioned was, but this one would be known unknown question answering sensors versus unknown situation awareness sensors. So I know it's a little bit of I don't know, semantic distinction almost, but just wanted to put that out there as a very early consideration and what it means to be a sensor.
Yeah. The other one I wanted to bring up, because this notion of question answering is pretty core. And the other way I would explore this is in systems where, so I mentioned this like notion of the bank robbery where you're actually trying to make inferences on something that happened in the past with sparse data. The other example is in systems that you want to non-invasively measure. Non-invasive measurement using non-invasive sensors is a really interesting one. One of my favorite examples there is the notion of actually being able to measure the tendon tension. So like if you have a muscular contraction and you actually want to know the quantity, like quantify that in vivo, the really interesting technique, I have a friend doing his PhD in rehabilitation robotics, and the very interesting technique he was telling me about is to actually effectively, you know how somebody has played a string instrument here, depending on the tension, it resonates at a different frequency. And so if you actually perturb the tendon in vivo, you can measure that kind of like relaxation frequency, and you can then infer the actual loading. So this is kind of an interesting roundabout way, right? Where we're doing a bunch of kind of like energy conversions and system models. And we have an active sensor, which is using the same transducer to create the pulse and then receive the information.
This reminds me of a similar technique. I think this was in like a spy movie or something, or a spy kind of thing, where you bounce a laser beam off a random surface in a room, and by like measuring the slight displacements and interference of the beam coming back, any surface that vibrates in an environment turns into a microphone. All you need to be able to do is point a laser at it and detect it coming back. I forget where I saw this, but yeah, that's kind of interesting. Just almost sort of jury rigging sensors right out of whatever is like available for improvisation in the environment, which makes it kind of like, astronomy type sensors. Like astronomy, you can't actually probe anything actively. It's like all far away and like huge stars and galaxies. But it's like literally they make use of all kinds of random effects to improvise inferences, right?
Yeah. So this is what you're referring to is the laser microphone?
Oh yeah. So window panes, mirrors, things like that. It's fun. It's like your tendon example, except for sound, I guess.
I kind of like this figure. It's an interesting illustration. This is a great like sensors, like academic paper cover or something, sort of like black and white cartoonography. But this is an interesting example. I will say, so this one is because we're actually measuring, I would actually liken the tendon ring down frequency, because really what you're doing is you're trying to pluck a string. That's really what you're doing. You're plucking a string and measuring some inherent oscillation to the system. This is very similar to how MRIs work. If I don't know how many of us are familiar with the kind of working notion of an MRI.
Yep.
If you
More or less. I would say the same thing. It's kind of like measuring the resonance of a oscillator, except it's at the atomic level, and we use a big magnet to kind of like make it ring. So it's like we have some inherent resonance phenomena that we perturb and then measure the outcome. The laser microphone, on the other hand, is literally measuring a deflection, which is a much more elementary thing. So we're just literally looking at a piece of glass and watching it wiggle, and we're measuring that angle at a very high bandwidth.
So the other extreme of this sort of phenomena that I'm trying to like think of now is how they measure the structure of ice caps. So like geologists who study like when the ice caps might melt. I remember reading an article of they drill a very deep hole into the ice sheet and basically drop a bomb in it. And that the measuring sort of the response of the ice shelf to the bomb gives you a sense of like where the stresses will propagate and how it might break off. So yeah, there's a whole bunch of these techniques, I guess.
So to perhaps bring it back to create relevant exhaust here for the Rover collective, because this is actually, I do recall, whose talk was it about Kubernetes?
I think Victor mainly talked about it a while back. Victor, yeah.
Oh, that's right. Yeah, and Victor looks like he couldn't join us this evening.
Yep.
But I think that there was some discussion there, I recall, which I think is super relevant, and it's the notion of kind of like distributed computing with a cost function of like energy, because we're working in an energy constrained environment on this other body. So if we're on let's say we're kind of on a lunar situation and we have finite amounts of energy, this question answering thing with energy becomes a very real consideration. And I think this impacts our sensor architecture choice pretty heavily. It also impacts the notion of distributed sensing, because it might be cheaper to fire up the radio and send some data between rovers if we're defining the system boundary as this software thing, instead of trying to do local compute that would be more intensive to like enhance more pixels or see behind the shadow, for instance. So I do think the notion of question answering as a function of energy and availability is maybe core to what a robust sensing platform will look like in a distributed rover context. Let's see here. I'm also trying to take some like little Rome notes here to tie this up. Are there any other constraints? So sensor availability and then power to inference, I would say, are two cost functions in a distributed rover sensing paradigm. Is there anything else that comes into play?
It seems like you would want to also consider like accuracy, because like you could pay more in energy to get more accurate results.
That's an excellent point. That's an excellent core sensors point. Accuracy is expensive. Always.
There's a very interesting example of this having to do with clocks, measuring time. You could call it a kind of sensing, though it's like on the boundary of is it sensing or not. But apparently, you can use the second law of thermodynamics to figure out that the more precise you want your timing measurement to be, the closer you get to the second law limit. And there's like I'll dig up the result and post it in your Rome notes. But yeah, so it's a second law limited phenomenon. Like precision is directly proportionate to the amount of energy you're willing or able to put in. So it's not a question of how clever you are. you want more precision, the second law says you have to put in more energy, at least for the case of time. For the case of time, it's proven. I don't know if it's generally true of other things, but perhaps it is. Like any measurement, the more precise you want it, the more kind of energy you'll need to get it.
This is true. And the other thing that I've seen to be very common in sensors is the notion of fixed bandwidth, which can be traded for accuracy, or like kind of resolution versus frame rate. That's just simply a product of frame rate and resolution is bandwidth, and bandwidth is usually actually the limiting factor in a lot of things, especially cameras. And a lot of camera sensors will support things such as binning, familiar with the notion of binning, or ROIs. So it's like maybe there's a good figure. I think it's a Sony part.
I shared the link about the clocks and energy in the chat.
Would the bandwidth thing be thought of as more of accuracy trade-off, because it's like the state of objects over time, right? Like more the frame rate, you have more accurate state, and yeah, and it takes more energy. Okay, it takes more bandwidth.
Is this in any way related to the bias variance trade-off, which is a statistics phenomenon? It seems like it would be related, but can't quite see the connection here.
I'm not
Would
sure.
the connection? I'm sorry. Would the connection be, the Nyquist frequency and the Shannon theorem that you need to sample at a high enough frequency to guarantee that you are not missing signal?
I think that's a special. I think that's a special case, because if you undersample from the Nyquist frequency, you'll get aliasing effects, which means there'll be multiple cases that you can't distinguish, right? So undersampling creates ambiguity, which is a kind of like increase in variance in like the signal you're detecting or something. But I think there's a couple of different phenomena being mentioned here, like this binning. It could be that that's the connection. Yeah, maybe.
Not sure. Huh?
Yeah, but I think there's a sort of family of interesting phenomena here having to do with quantization, sampling limit theorems, and sort of the statistical techniques being employed, like binning and things like that. So there's like 2 or 3 things going on here at once.
Yeah, I mean, I will say, so I'm definitely referring to just simply. So this is the common example, and I don't know why I'm having such a hard time finding a good example. Okay, so the premise is we have all these sensors that are just getting increasingly higher and higher resolution, but we don't care because we actually want to be able to go at high speeds. But then we have all these vehicles doing autonomy things, and we have a lot of drones that need stable video, and we want stabilized video. So why can't we simply get a really, really large camera sensor and then only read out the part that we care about? Because for instance, if we want to have a single front-facing camera on a car, but we want to look very, very, very far down the highway, because when you're trying to do trajectory planning in an autonomous car, you want to be able to look into the future, and the future happens to be a very, very narrow, field of view when you're on the highway. So you want to be able to read out the entire frame, maybe let's say once every 1/15th of a second, and then you want to check out stuff that's interesting at a higher frame rate at maybe 60 or 90 frames per second. And you can achieve this with sensors that allow you to say, I only want you to read out this section of the die and then put it in a buffer or whatever, and do that at 2 different sample rates. And this allows you to do this kind of like dynamic, checking out what's going on. This doesn't really get into the Nyquist frequency, because this is simply a temporal phenomena that we're trying to control. So we're trying to get a higher frame rate for fast moving objects or things that are, oh, actually I just stepped on myself there. Because this is my point. If you're trying to bin a sensor, are we all familiar with the notion of binning?
I am.
So
Yeah.
binning is just,
I know what it
Binning is-
means for just any data, but like, yeah, for a sensor.
oh, like so specifically for a camera sensor, binning is just grouping up blocks of pixels. So it's like if I have a 4x4 camera, very, very small camera, and I'm running it at no binning, like 1x binning, I get the full 4x4. If I do 2x binning, I get a 2x2, and then if it's 4x, I get a single pixel. And that allows you to, in a lot of sensors, that allows you to average the signal together, because the noise is distributed across the sensor, right? So you get a lower noise estimate of the signal. But then we get into our Nyquist frequency thing, because if we're looking at something that's very far away and we want to have good spatial resolution, we need to not bin, because following that law, we can only measure a particular kind of like edge rate of change, or like spatial resolution of, let's say the light post is, let's say we're trying to read the speed limit sign very far away. We can only make out that typeface if we have, like, say, three pixels or whatever of width. If you bin that down, you lose it. So yeah, what I'm getting at is so a lot of these sensors, if you bin it, it runs faster. And if you do an ROI where you look at, it's 1 pixel, it's this full resolution, but a small section, it's a readout thing. So it's a bandwidth thing to just read it out. Because a lot of these sensors, they build up the signal and then they have to digitize it.
So a very interesting, but completely different type of example of the same phenomena is the way they're doing COVID testing now. So I forget what the technique is called, but you do the batch testing of like, you test for positivity in like pools. I think it's called pooled testing. So if you have like limitation on the number of tests you can run, you basically mix up the samples from like multiple people together and test the whole thing. And if it turns out positive, one of the tests is positive, and then you further in high resolution effectively redo the tests on those. So it's a good way to budget. Like if you have like if you have like 10 COVID tests available, maybe you use 8 of them to test, say, 32 people in batches of 4 each. And you hope that less than 2 of them will come back positive. And then you kind of like use your remaining budget to probe those or something like that. So I think it's a very general strategy, which makes me suspect there's probably statistics and Nyquist and Shannon stuff going on there that's like abstracted away from the specifics of the sensor. Like, yes, cameras are a good example, but if it works for like disease surveillance as well, chances are there's something general going on.
Yeah,
So
that's a
there's
great
a difference here too between binning and sampling, right? Like, so if I had a camera sensor and I was sampled, that would give me a different answer, because you're not averaging multiple data points together. You're just like grabbing a distinct data point. Is that ever a consideration for those sorts of things? Like I think about sampling across time, I guess, more frequently.
I'm not sure I totally follow. This is just where and when we would do, because there's a few quantities, right? It's frame rate, resolution, and then noise. Those are usually the big quantities that you're juggling with these sensors.
And I think you generally make an assumption that your sensor is much faster in terms of time constant than the phenomenon it's measuring. So like a CCD pixel will have a particular drop-off rate of the potential. Any sensor will have that kind of thing. And you typically want it, I think a good heuristic is like, you want its bandwidth to be like 10x the bandwidth of the phenomenon being measured. And if they come too close, then you get, again, sampling and like Nyquist crap going on. Like if you're doing a camera thing and have you seen those photographs of fast spinning propellers? I just saw good examples on Twitter. So this is specifically having to do with when you try to photograph a fast spinning propeller with a digital camera that's raster scanned, the interaction of the scan rate of the raster algorithm and the rotation rate of the propeller will create really weird distortions. So it's not like old fashioned, oh yeah, there's a bunch over there. Look at the helicopter rotors there. So that's the kind of thing you get if your frame rate and the phenomeno's fundamental frequency get too close. So remember, this is not what you would get with like too slow of an analog camera. This is specifically a raster scan digital camera effect. It was really weird. Like somebody just posted, I
These are
think,
some good ones.
somebody posted a simulation of script for this on GitHub. That's how I saw it. Like somebody was tweeting about it. So yeah,
Yeah,
that's the one I saw. The red one.
Solid tweets.
What?
Yeah.
It's pretty counterintuitive actually, but there is a simpler example than the propeller one. It's I guess most of us have tried to take a picture of a television at some point in our lives, and you know, the image is really flickering. It's pretty hard actually to get a nice picture of a television with a digital camera. You see the problem?
Yeah, that's the basic stroboscopic effect, right? Where you get the banding that scrolls slowly across the screen.
Yes.
Yeah, so
But
this
also
is
a television is also a raster scanning, plus the camera also raster scanning.
Are we all familiar with the notion of a global versus rolling shutter?
No.
Oh, really?
No, I don't know.
So this is a good this is an awesome video that shows how a DSLR actually takes a photo. And this also, I don't know if anybody has done much photography specifically with DSLRs and flashes, but what will happen is you'll often get a DSLR and you'll see that there's a maximum speed called I believe it's usually referred to as like the strobe sync speed. And it's usually about 100th of a second or 125th of a second. And what we just saw here is there are two curtains that open up over these sensors. And these curtains have a specific rate at which they can open and close because they're mechanical devices. And these curtains open at about that speed, because what happens when you go below that speed, and let's say you're shooting at 1/1000th of a second, the curtains do not completely open. It doesn't open one then the other. They actually follow each other, and there's a slit of the sensor exposed at any given time. So if you flash the strobe, it actually will only expose a small portion of the sensor at a given time. And the way around this, because you'll see all of these point and shoot cameras and DSLR cameras that allow you to shoot with the flash at higher speeds. The way around this is they'll actually shoot the flash multiple times when you shoot above that 1/100th of a second. So it fires the flash maybe like 100 times, and it exposes the sensor all the way down, which is kind of an interesting hack. The notion of global versus rolling shutter is very important to sensors, though. Let's see what Google has to. That is not what I was looking for. I'm sure, there's a great example. This is fine. Okay, I mean, the difference in the performance is clear, right? One, we have a distorted image, and the other, we have a clean image. The difference is simply that in the rolling shutter, the sensor actually reads out the rows sequentially while they're still getting exposed. The global shutter, it captures all the photons at once, and then it holds it and reads it out. That's the difference. And this is often very important for autonomy applications, for fast moving objects, because you could imagine that your classifier is going to have a really hard time between these two things. Or if you have an object that's moving quickly, the person who's on a bike that went past the front of your robot is going to be smeared or skewed. And unless you've trained your network on skewed people, it's not going to know what a skewed person is. So it's in your interest for your system to be utilizing global shutters to get around this unfortunate artifacts here. Because yeah, like I think the network would have trouble with that.
Why are there rolling shutters?
You're cheaper.
Is it like a bandwidth issue or it's a sensor issue?
That's actually that's above my pay grade at the moment. I haven't. This is actually something I haven't had to look into recently as to why that is. Is anybody else? Would you happen to know, Venkatesh, through any of your work, the main cost driver difference?
No, this idea of global versus rolling shutters is actually new to me. I hadn't heard of it before.
Oh, really? Oh,
Yeah.
well, great. Yeah,
I've used SLR cameras, but I've never bothered to look into how they work.
Yeah, same.
This is a great. Yeah, this kind of sums it up. So there's the Porsche and the skewed Porsche. That's the difference.
This actually vaguely reminds me of what you were showing last time, Rhett. With your cheap camera, you had the weird artifacts of like dropped bytes or something, right? And
Yeah, but it's like it's a bit for that it's a bandwidth issue, except that like you're storing everything on the chip, and then you've got all this time to pull it off. But it's at least storing like a static image. That's done somehow. Like I don't know, even though it seems like, oh, I've just got this little sensor and this chip, and there's still like so many layers that are happening on this $10 chip that I have no idea. The data sheet's all in Chinese, so who knows?
Oh no. But yeah, so like a lot of applications, it's okay. So I think for like the Yak Rover stuff, I actually don't know if you would ever really need a global shutter, because it's usually things are moving pretty slowly. Right, this is a relatively slow moving environment potentially. So yeah, okay. So we talked a little bit about sensors. So, well, cameras. Getting into cameras. The general trend is everybody's trying to go to vision. I think this is most well known through the Tesla publicity machine. I hope everybody here watched AI Day. There's some very good discussion, and just on a lot of topics, especially topics concerning vision and pipelines for vision, and especially pipelines, again, to this question of like, what are we actually, like the question of what questions are we answering? Like, what information are we seeking? The big one there was the notion of, that's actually a good thing to touch on. So there is this famously, talk about Tesla for a minute. I think very famously when Tesla was using the Mobileye system and the performance was inadequate, Elon was trying to recruit George Haas to come on board and actually build an autonomy system, because he was messing around with monocular smartphone-based self-driving car stuff in his garage. So I think you want to ask some question about like, would you ever do compute on the camera? And I think George Haas was like, yeah, you totally could. And it would kind of like lower the bandwidth requirements back to the main compute. Now, this is actually a total blunder answer. And there's a number of reasons why. And if you watch the AI Day talk, it really kind of touches on it. The biggest one is very often you are trying to perform inference on data that spans beyond the bounds of a single camera. That is like the big thing. You want to run your inference on the 360-degree perception of the vehicle and not individual disparate images, which then are getting potentially kind of like stitched together. Because it'd be like, I saw half of a car, I think, and then the other camera says, oh, I also think I saw half of a car. That would be a way easier question to answer if you just could fuse it together, feed your pipeline, and then just look at the whole freaking car. So this notion of distributed compute versus centralized compute, that really becomes pretty obvious what you have to do there. And it also gets to the point of like, what does a fault tolerant system look like? If it's centralized, then it just kind of inherently gets answered that you need to have redundancy in the centralized compute. So you need to have centralized redundancy in order to do everything that you need to do. And an application such as on-road autonomy, where it's not safe to be like, I'm not sure what that is, I have to stop. That's actually a really big difference between like automotive autonomy and a lot of other autonomous applications. Like a lot of other autonomous things, if they're not sure what's going on, they can just be like, I don't know, and stop. Cars do not have that luxury. And so that's why it gets just, the stakes are way higher, and you have all this redundancy and fusion. So yeah, this is all to say that on-camera compute, there are some places where it just doesn't work. And it's unfortunate because there are actually a lot of really cool little like embedded compute modules. I think Mayer brought up the Movidius, or no, I think somebody posted, somebody posted that there's a new cheaper
the Oak D light.
Yeah, the cheaper light. Yeah, the Oak.
Yeah.
That runs on the Myriad X, right?
I don't know if, I think they have their own processor. I don't think they are
it
using
does.
Myriad.
It's a Myriad X.
Ah, okay.
Yeah.
There are very, very, very few people in the world that make vision processors.
Okay.
It's just Intel and NVIDIA. That's it. There's really nobody else. It's actually a little bit frightening. It's kind of unfortunate. But yeah, the Oak is all the Myriad X as well. And yeah, so I'm personally a little bit skeptical of on die compute or on sensor compute. And I was talking about the notion of doing dynamic region of interest, like higher frame rate region of interest. That is usually something that you start to talk about when there's bandwidth limitations. But if you're working in the 3 to 5 year timeline, maybe bandwidth isn't a problem, and it never makes sense to do any inference or compute on the camera, and it all just goes back to a central platform. So in terms of where we're actually doing this compute, that's I think it's kind of an open question, but for especially cars, it has to be centralized. So centralized versus decentralized, when default tolerance is you can't stop, it has to be centralized. For the Rover stuff, I don't know.
So the other extreme of this, I guess, dimension of design space is something like a distributed sensor network on a much larger scale. So you have a huge number of UAVs that are like search and rescuing on large national park where a hiker has gotten lost, or searching for a terrorist in a large geographic area. So that physically, by necessity, all the cameras are separated on different vehicles that are like way far apart. But even there, you get the trade-off of, on the one extreme, you have things like interferometric telescopes where it does actually make sense to move the raw data. So this is not even like fusing the sensors at the level of sample data. So interferometry is when you're literally interfering the light waves, right? So I think of that as one extreme of fusing the data together. Somewhere in the middle is you do low-level sample data and then compose the overall image. And at the far end, maybe you've got a bunch of UAVs and you're searching for something small that'll fit in the field of view of one UAV, a tank. And you want to form a picture of how many tanks the enemy has. There's no particular reason to not do the inference on the sensor itself, because in this case, it's sort of the sensor equivalent of an embarrassingly parallel problem. So I think this is basically a question of what kind of data structure is there in the thing you're sensing. So whether it's embarrassingly parallel or not. But if you're looking for tiny dots on a large canvas, then it's embarrassingly parallel sensing problem. But if you're looking for something with a lot of large scale structure, like half a car on one camera and another half of a car on another, then yeah, it makes sense, I think, to pull it together. So I would say that it's interesting to look at this beyond like autonomous driving, because that has the danger of becoming too much of a I don't know, single application that shapes. I don't want to over-index on autonomous driving, because like rovers, for example, depending on how you deploy them, you could have 100 rovers scattered around like 100 square kilometers, and you're doing like, I don't know, soil characterization with cameras, like just looking at the color of the soil, and you're trying to build a map of like what the soil is in different parts. There, I see no reason not to do like on-camera compute or like on single rover compute. But yeah, if you're trying to map the shape of a mountain, maybe you should like fuse it together first.
There is this notion of scaling to that which is sense and that which is sensing. So like a improperly scaled sensor to like object you're trying to detect, in the case of the car that spans out of the sensor field of view. Potentially in the rover application, if you know what you're looking for or have a pretty good idea, you can just correctly scale the sensor so you don't have this problem, and then on sensor compute is super easy. But I think if the question is you don't know what you're looking for, that's where you have issues. And you can always do something like the fisheye, where you have the very, very large field of view, but then you start to run into that inherent that resolution problem.
I think Perseverance actually solves that with 2 antennas when it comes to communicating with Earth. I think we talked about this at one point, it's in the book, but there's a sort of very coarse, sort of high field of view antenna that looks for Earth. But once you find Earth, there's like a narrower field communication beam that you then point at it. I forget the exact details, but it's like a 2 antenna system for communications. So
it's like a high gain antenna has to be very directionally aligned.
Yep. And I think the same thing happens with the rover missions that talk to an orbit station, right? Where you kind of have to like communicate in bursts when the orbital station is passing overhead or something. So yeah, general principle there again, same general principle.
The notion that I've talked about with a couple people that I think is interesting is the notion that cameras and just ubiquitous cameras and cameras being pointed everywhere on robots is actually what will take the place of skin on robots. I think a vision-based skin is something that we'll start to see a bit more. Yeah, I think the best example there would again be the Tesla kind of like their security system, where it's just a spatial kind of like keep out that they then kind of activate the flashy lights and the things. But it's just this notion that vision can actually be used to perform a lot of other things and start to eat sensors. So yeah, I would talk about that for a minute. It's like, what sensors are eating what sensors? The most famous example is LiDAR and cameras. That's just a constant war zone. But what other sensors can we kind of see eating each other?
So I find it easier to start from the other end, which is what sensors cannot eat other sensors. And one problem I've been sort of like casually sort of at least observing for a long time is diet apps that attempt to infer the caloric content of food from just images, like take a photo of a plate of food and try to find out like how many calories and like, fat, protein, carbs it has. And I've talked to several people about this problem over the years. And the basic conclusion is that it's impossible because, for example, the oil content of a piece of food, the only way you can get at it from vision is like the gloss. And the gloss could be from moisture, it could be from oil. And apparently so far there isn't like a good way to do it, but maybe machine learning can solve that. So that's an example of like a hard to eat with vision problem. And I think that generalizes to anything where you're trying to infer material chemistry and composition from visual data. But what else?
Yeah, maybe we could introduce the notion of a sensing catalyst, because my favorite example in the home health space is I don't remember the name. This was wow, I can't remember, but it's an in-home urinalysis kit where, because you're trying to perform some assays on a urine sample, right? And you could argue that that requires a specific set of sensors, which is just extraordinarily hard to get into an at-home setting. And so the catalyst here is an intermediary transducer, which is a colorimetric test strip. And simply taking a photo of a test strip is about half of the problem getting solved. Is it like healthy.io?
Oh, so I guess a simple example of that would be actually like a litmus strip. You insert it into an unknown liquid and you actually detect whether it's red or blue. So that sort of strategy.
Right, but I think the last detail that they figured out was if you just take a photo of a test strip, that's relative data, but not absolute. So you need a calibration target. And they simply just provide this color calibration target, which allows to have light invariant, like quantitative data. So you simply, because otherwise this would be an impossible task, and you try to be sensing things with a piece of lab equipment. So you first convert it from actual chemical assay into color and the visible spectrum, and then we go ahead and get an absolute baseline for that color with the reference target, and then we can use our vision-based processing pipeline to get an actual piece of test data. So this is, I just view this as a sensing catalyst. Is a test strip where we usually are doing some chemistry to convert quantities into color.
So I don't know if catalyst is the right word. This looks like two sensors in series to me. Like the test strip is a sensor and it's converting from like one form, so chemical energy, to like visual spectrum energy, and then the second sensor is in series with it. So why are you thinking of it as a catalyst?
It is correct that it's two discrete, it's like they are discrete steps and they have system bounds. But in terms of what we're actually trying to detect and what the final endpoint is, I'm just kind of binning, for the point of discussion, all the intermediary conversions into a catalyst. So like the thing that's the ubiquitous sensor here is, again, cameras. And then we had this notion of what sensors cannot be eaten. And I'm saying like a pH, like an actual, laboratory pH detection, that is a sensor which is very hard to replace when you would initially think about it. But if we introduce a test strip, I'm just saying in terms of like coinage and how to think about using intermediary conversions, I'm calling it a catalyst. Maybe that doesn't really make sense.
I think there's an element of catalysis there, but what it's catalyzing, I think, is the location and cost of the sensor. So you're using the vision as an intermediary to move an expensive sensor from a central location to a cheap sensor on a peripheral location. Something like that might be what's happening. So it's some kind of unit economics transformation thing that's mainly going on. There's something else here that's like vision, in the way you're talking about it, is almost like what happened with electricity and like then with discrete electricity, like between 100 to 50 years ago. Like instead of measuring like some other signal, you measure it locally and then convert it into electricity, right? So a mercury thermometer, you're measuring temperature through like a rising column of mercury, but you can convert it to electricity using a thermistor. So that's like you're using electricity from like contraction. So electricity kind of, you could say vision is eating sensing, kind of like electricity ate sensing 100 years ago, or 100 to 50 years ago. But yeah, I mean, there's an element of catalysis here. I don't want to like worry about the semantics point. I'm just trying to get at the essence of it.
Yeah. Yeah, I mean, in terms of timeline, though, I would say vision is the thing that's eating the other things because it's most novel. It's newest. So it's like that's a contemporary sensor, which is now allowing this to crawl out of the lab. Test strips are very old. Eric just left and came back in. I think he's back in now. Okay. Yeah, so like color strips are very old. Cameras are quite new. To me, the novelty here is the calibration target, which was just potentially a non-obvious way to actually get qualitative data out. But yeah, like, okay, so maybe, yeah, the intermediary step, maybe that's the better question, because there are a lot of sensors that are portable, but then is there a conversion that's missing? Like what conversions are missing? Because the example there is like, you can retrofit old sensors using like vision as an example. So it's like if you have an old gas meter that traditionally gets read by a person walking up and reading it, you can now just stick a camera on that, and the camera these days is what's the ESP? We use the ESP cam. I think that's the cheapest camera with compute that I can think of. Anybody played with one of these?
Yeah, I have.
Yes. Yes, here too.
So you stick one of these on the front of your gas meter, and then you can read the gas meter. So you now have actual quantitative data out of the gas meter using vision, plus compute, mind you. There's some compute that's required in order to actually get the question answered and get the quantity. But the intermediary step here is taken care of because it's human readable. I think as long as it's human readable, maybe that's it. If it's human readable, it can now be consumed by vision. I don't know. I'm just riffing on this notion of sensors eating sensors, because I do think it's a fair point Venkatesh should talk about or attempt to talk about sensors that can't be eaten.
Yeah. Again, I like to always go back to biology as sort of the canonical reference point. Like human biology has converged to like 5+1. I don't know whether or not to think of proprioception as a sensor, but I think of it as 5+1. But yeah, even there, I would say vision, at least in all primates, has strongly eaten all other sensors. Whereas if you look like at canids and felids, smell is still a highly dominant sensor. But in primates, it evolved because of the omnivorous, like fruit-based diet, and like telling the colors of fruits apart turned out to be an important enough driver that vision became much more powerful. And then you had other things like the human social capability. A lot of it is reading visual cues on facial expression. So like the flushing response, like your face turning red a little bit, that's like something that humans are slightly adapted to. And you kind of detect whether emotions are authentic or not based on whether the face is flushing or not. And that's something some people can hide, some people don't have a strong voluntary flushing reflex, other people do. So that's an example, you could say, of biology discovering this design pattern of make the emotion sort of translate an emotional state into a visual color state in terms of skin. So people know whether you're actually angry or pretending to be angry and respond appropriately, right? But so I think there's like biological precedent for your line of thinking, sensors eating sensors. But I'm trying to think of what are cases where other sensors have done a lot of eating. Like I think smell is the other hugely dominant kind of sense in many animals.
Smell is, yeah, that is an unsolved. Yeah, that's a really hard one. Yeah, that's one.
And smell, I would say, is not even a single sense. It's a meta sense of like dozen different receptors for like commonly encountered molecules, right? As far as I know, I don't think it's single or like there's no generality there. Smell is a bunch of like custom sensors.
Yes, there's a lot going on there, and it also is something we really have not been able to package to the extent that biology has done so. So you do have things like gas chromatographs that can do some of it, but not anywhere near the bandwidth and portability of the dog nose. Has everybody seen the camera-based heart rate detection using color amplification? Really? So I think one thing that's interesting to talk about is superhuman sensing. Yeah, this is a classic. Let me put this on Discord. So this is where we're actually amplifying. They're doing a bunch of frequency domain amplification, both in deflection and color. And the really interesting one is color, because there's a practical application. So that's an actual video that's being amplified in the particular color channel.
Wow. Okay.
And this allows us to take people's pulse from across the room using a security camera, let's say.
I had not seen this. So this makes me wonder whether humans are actually unconsciously able to detect this. Like you may not consciously realize it, but maybe this is why some people are good at detecting people lying.
Interesting. Because the other one, so the two ones that you get pretty easily are respiration rate and heart rate. And there was actually an iPhone app that Philips put out a long time. I think it's no longer in the App Store, but they had this. It was an iPhone app where you could sit there and point it at your face, and it would run the algorithm and tell you your respiration rate and your heart rate. It was really kind of a technology demonstration. I don't really know why the app existed, but it did actually show it working with just a consumer smartphone, which is kind of cool.
So if you put this on Zoom, you can tell who's lying in a meeting and who's. I'm still trying to like synthesize a lie detector out of this.
Yeah.
Speculatively.
Yeah, but this is definitely, I view this as a superhuman application of vision. If we're talking about sensors eating sensors when it comes to things that humans can do with their vision, what can't we do with our vision? And this is an example, I think, is this kind of like selective amplification. There are also sensors that can see at night better than us now, which took a long time, but can do it now.
So this kind of supersedes the point that you need the intermediary step to be human readable, right? Like, so it could be still machine readable. The humans might not be able to sense the intermediary step.
There's some work recently that I saw on machine learning, compression for machine learning. So when you do compression for things like JPEG, typically those algorithms are optimized for minimizing lossiness for human perception, right? But that's not necessarily the right way to compress if you're trying to learn for machine learning features. So people are now like sort of undoing JPEG style human targeted compression algorithms and sort of figuring out how do you compress like raw imagery so that machine learning works better. So I think we're going to see more and more of that sort of thing where you start optimizing not just the sensor itself, but the sort of stack of low-level processing layers right after the sensor, you're going to start optimizing it more and more for what helps the machine the most as opposed to humans the most. And so in some cases, both. Like, I'm trying to think, like, since we're talking about biomarker stuff, like it intrigues me that heart rate variability, or HRV, has somehow become like the holy grail gospel signal, and all these devices seem to infer everything from like infection state to stress to whatever the hell using heart rate variability. And that seems to me a little bit alchemy, because there's no causal theory of how you correlate variations in heart rate to various like complicated things, but apparently you can. And maybe there's versions of that in robotics, like throw a bunch of sensors on a robot and through some mysterious alchemy, something like heart rate variability pops out as like your rover's health measure.
I would say HRV is the hot metric in like kind of physiological marker measurement, just because it's a commoditized sensor now. There are several silicon companies now that will just make you a package that you put a photodiode and an LED on it on your board, and it just freaking works. And you don't have to hire a team to develop that. So that's like a commoditized sensor. And there's the most plausible deniability that you're making things up with HRV.
Yeah, I was finding myself suspecting that half the HRV stuff is kind of like just made up bullshit. Like, I don't believe half of it, but I don't know. Maybe there's something there.
It is worth mentioning. So we're talking about biology. Most biological sensors are passive. I think the only one that comes to mind is echolocation is an active sensor. Everything else is passive. I think you could say our tactile sense, maybe that's active. Maybe this is a stretch, but the one I always think is interesting is the topic of rummaging. This is a topic that Ken Goldberg at Berkeley has done a lot of research in. And is everyone familiar with rummaging? Like, what is rummaging?
Like just, do you mean just like putting your hands into a bin of random crap and like stirring it up to find stuff? Like the
correct. And that's a vision denied environment, right? So it's completely occluded. And this is why it's interesting. It's trying to teach a robot how to rummage because it's a completely occluded environment. So this topic of rummaging and how we actually use strictly our sense of touch combined with our, actual actuation of our appendages. This is like an interesting sensing topic because it's kind of like a sparse sensing environment, and we're also reliant on the non-dominant sensing modality for apes to actually get the task done. So there's a lot going on when it comes to rummaging.
There's apparently a Chinese game based on that. So you take a bundle of sticks and one of them is broken and you wrap it in a piece of cloth with a string. And apparently the game is you just have to feel from the outside and figure out which of the sticks is broken. So apparently it's used to teach, monks trying to develop their sort of meditative mindfulness or something, how to like sense inner states through just feel. So it's like a training exercise for monks. So I would call that a rummaging game. But I think it's interesting that you're making the claim that most biological sensors are active. I would say something like are passive, but I would say, in fact, what's happened is that the active component has sort of been, has evolved into sort of a general shared resource. Like the most important piece of active sensing is positioning. So touch, vision, ears, everything can be positioned sort of in rotational orientation. You move your head and vision and ears move, and you move with your feet, and you can actually just plant the sensor somewhere else. So that's one element of activity. The other element of activity, I think, is just outsourced to the brain, as in what you're paying attention to. So if you're like, right now, I'm like looking at my two hands, I'm not focusing attention on any of my fingers. But if I decide I'm going to pay attention to my right forefinger, suddenly I'm more acutely aware of that. So the brain does a lot of that, like just focusing attention on the right part of the sensor network. So in that sense, there's two kinds of like active sensing that are like that are part of like shared capability. But yeah, you're right. The actual sensor itself is not active.
Right, in the strict sense of physics, it's not. And I would say it's actually interesting that you bring it up, because this is kind of like a neural region of interest that we're performing. Is in effect, we're attenuating all the other stimulus in a controlled manner.
Yeah, and when people go blind, their sense of touch improves. That's why they're able to like read Braille and things like that. So it's like there's a lot of neuroplasticity that sort of, I would guess the way to think of it is neuroplasticity reprograms the sensor payload at various time scales based on like both reversible and irreversible changes. So at night, maybe your hearing becomes more acute because your vision is compromised. And if you get deaf, your vision might improve. If you get blind, your hearing might improve. So there's a lot of like programmability in the higher layers of sensing.
I'm trying to get my head around active and passive and actuation. For example, in rummaging, it seems like a task wherein you have an actuation component also, right? Like you are sensing it with that sense of touch, and you're trying to form a mental model of objects unconsciously or consciously inside the bin, and then trying to find. So in a way, while you're trying to move your hand around the bin, isn't it more of an actuation rather than just sense? What is it? Just sensing. So it is like trying to accomplish a task with sensing and actuation, and it seems to be tying up to me to the abstraction question, like what do we, the abstraction layer of the sensor, is rummaging a sensor, or is it more of a task wherein which can be decomposed into sensing and actuation steps?
I think the best example of this combined sensor actuator in biology that we could potentially talk about being a gray area of passive versus active sensor are whiskers. Whiskers are actually kind of an interesting sensor because they require like movement to really do their job super well. And rodents do this a lot, where they'll actually move around their whiskers to perform the whisking, which then allows them to build a spatial model of whatever they're in front of. So yeah, that might be a good example of a coupled sensor actuator in biology that forms effectively an active sensor is whiskers.
I think one way to think of this more generally is not the active or passive state of the sensor in isolation, but in relation to sort of the energy transformations of the environment, right? Like when you do like a harmonic characterization of like just a solid object, like how it vibrates, you can't actually do it without actually disturbing it in some way. So you would typically do an impulse response, right? Like you would hit it with a hammer. That's what a tuning fork kind of thing does. And then you would sort of measure the response. So an impulse response is kind of like an active sensing tactic that's dictated by the nature of both the thing you're sensing and the thing you're sensing with. And you could talk of things like rummaging as like generalizations of the concept of an impulse response, or like injecting like a white noise. That's another strategy. So impulse and white noise are the two most common things you inject into an unknown plant to detect what's going on there. So rummaging is like almost injecting white noise into a bin of objects and sort of developing the frequency response of that. Like quite literally, you could actually like systematize this in a dumb way. Like maybe a rummaging strategy could be you shove your hand in and like first try to move it very fast, then try to move it a little bit more slowly. That gives you like, a frequency response quite literally. Like if your hand can move more quickly when it's moved fast as opposed to slow, maybe the objects are small. So it's a very sort of coarse generalization, but I think the concept is actually the same. It's impulse responses or white noise responses at the level of abstract objects.
One interesting thing about whiskers is they do work in vacuum. So this actually might be kind of an interesting sensor to put on a rover. just due to this kind of like kind of robustness to this environment, the space environment. Yeah. So let's see. Yeah, I do think maybe to talk about to kind of close out this notion of sensors eating sensors. There are a lot of sensors that are just straight up unnatural. So like one example is LiDAR is something that is extraordinarily unnatural, or is something you would never really be able to emulate with organic structures, probably. The other one is something like X-ray fluorescence. That's an very interesting sensor that is also kind of in spite of nature. So, but the irony is, while LiDAR is this amazing thing that's kind of like against nature, vision is even now today being sold as something that can supplant LiDAR in its kind of like superhuman, unnatural form, which I think is pretty interesting.
So there's an angle of like natural sensors eating unnatural sensors.
Yeah, it's actually a pretty interesting one. Yeah.
Like Elon's justification for his whole famous posture is literally that humans can do it without LiDAR. Why do we need LiDAR? Like that's the simplest version of the argument he used. But yeah, I mean, I don't know. I kind of like sensors just for the sake of sensors. So I like thinking of like the unnatural ones, because it's the more extreme the regimes of things you get into, the more extreme your sensing also has to be. Like think of something like, LIGO, the gravitational wave detector.
Oh yeah.
There is no conceivable reason, at least for human or like Earth-style biology, to even need to sense gravitational waves. So it's like something that came at the end of like a century of physics to even think about wanting to measure it. And then you come up with the most sensitive instrument in the world to do it. And it shares some operating principles with like vision in some sense, but fundamentally it's a completely weird thing. It's a Rube Goldberg machine to detect gravitational waves.
That is worth mentioning as just a trivia point, that LIGO is the most sensitive thing we've ever made, by quite a lot, actually. I believe it's 10 to the 20 or 10 to the negative 20. Yeah, it's pretty neat. Most sensitive thing ever by several orders of magnitude.
Yeah, like you also have to compensate for the cars driving around, maybe.
Yeah, exactly.
I think
so
the question of natural sensors eating the supernatural could be thought of as, in self-driving cars, it's easier to annotate the data. They need humans to annotate the data. And it seems like vision is more easy to annotate than LiDAR signals or something. Would that make sense? Like in contexts where you need annotation from humans, are some places wherein natural sensors can eat the supernatural sensors because of the scale of data that is available.
I mean, annotation is, I would argue that's really a task that's relevant to questions being answered further down the pipeline. Like that's after the actual sensing has been performed. I think you could probably argue against that. There's a counterpoint there of like, is it a human or is it a mailbox? Like that, maybe that's an actual part of the sensing question. But actually, if you read, if you watch the Tesla AI Day presentation, they do talk about annotation quite a bit, and the annotation team, and they still annotate in 3D now. So they're still annotating even in 3D data. I mean, the 3D data is easier and higher throughput for humans to annotate, but it's not like it goes away. To kind of close the point about like these contrasts of sensors, and we have this like spectrum of natural versus unnatural, especially when it comes to camera and LiDAR. going all the way back to what I was saying in the beginning about direct versus indirect measurements. LiDAR is a direct measurement. Cameras are an indirect measurement, and all of the effort that's gone into computing depth from cameras it's like it requires an incredible amount of compute on top of the camera raw data to try to get the same results that LiDAR gives you. That's the main argument in favor of LiDAR, is it gives you a direct measurement, which is, way more robust in a lot of situations. So that's why there's this war of like, well, humans can do it with just 2 eyes. What if you gave them 8 eyes and no alcohol? Versus like this notion that LiDAR just measures it point blank without error. Like there's no question. It's a direct physical measurement. So that's like LiDAR is superhuman, but the data is simple. Versus cameras are very natural, but the data is complex. Maybe that's a logical conclusion, just given how complex our vision system is in the brain. Like there's a lot that goes on there, so maybe that is actually it does fall naturally. But to me, at least, it seems counterintuitive at first glance.
A quick time check. We should probably wrap up in about 5 minutes. I'm going for about just over an hour.
Do you think that there is maybe perhaps the other reason that vision is such a important sense is that it works so well for humans to understand it that like we have essentially a technology dividend from smartphones and miniaturization of just like really great cameras getting better and better all the time, whereas relatively less investment is made in audio sensing because we don't necessarily rely on it in the same way.
There's a let me double check. I think that's public. Yeah, I don't know if the name is public. Anyway, sound is an interesting one because you can use sound to detect in the most elementary form, just raw distance. But it turns out you can actually do way more complex things, such as actually track hands with ultrasound. So this is kind of an interesting thing where sound actually can be used to do quite a bit more sophisticated sensing that you may initially think, by using a more complex arrangement of detectors and emitters.
Related to sound, we can talk about earthquake detectors as well. On similar principles, it's very hard to replace an earthquake detector, basically.
Just because of its accuracy and precision?
No, just because it's of the what it's measuring. I mean, right now I can't see how we could replace an earthquake detector, like a Richter scale or something like that. How we could replace that by a camera system, for example, because it would be too late, basically. It would be too slow. Here in Japan, we have earthquakes like every other week. Okay, so many of them, and the thing that we can see the buildings dancing. Okay, so we could think that we could use a camera to detect dancing buildings, but we can see the buildings. Minutes after we got an alert for an earthquake, basically, based on sensors that measure vibrations, some vibrations in the earth, in the crust, basically. So I'm just drawing a parallel with the sound, where sometimes sound is a vibration as well, okay? And so there are cases where sound is very interesting, or vibrations are very interesting because of their peculiarity in a way.
I would actually push back on that. That's an interesting thought, because the camera could probably, with the inference and everything, do the detection at a similar accuracy of an event. So it's like if the question that we're answering, again, in terms of like, what's the question we're answering? Is there an earthquake above some magnitude? That's probably a question the camera could answer to a low level of kind of like accuracy. Precision. The accuracy would probably be good, but the precision would be low. This also comes back to like sensor kind of like sparseness. So the example there is detecting wildfires. I think somebody recently wrote a Twitter bot that scraped live streams from several wildfire lookout cameras in California, and they just ran a model on those live streams, and they actually ended up doing a pretty good job of detecting wildfires pretty early, and they had their bot tweet about it.
But wildfires are a fundamentally visual phenomena, that they have a visual signature, whereas earthquakes, you kind of have to like convert solid vibrations into like some kind of much more visual signal, like a dancing needle or something, before a camera would be useful, or improvise it, like, train a zoom lens camera on a very distant object and see if it shakes. So you'd have to go through contortions to do that. And speaking of your wildfires example, the example I would push back with is, I think there's a startup doing deforestation detection in the Brazilian rainforest. That's basically a sensor network of microphones. It's easy to like detect the sound of like chainsaws and stuff. So
yeah, I know those guys kind of.
Yeah.
Yeah.
So I don't know. I think I'm with Eric on this one. Earthquake seems like a little bit of a stretch for camera eating seismographs. But I would say, okay, if you kind of like make up a game of, you have like a sparse sensor budget and you kind of have to make do with whatever, and if you could just have one kind of sensor, what would you do? I would say having a bunch of cameras is probably the most versatile, because you can infer a lot from like cameras doing complicated things. So yeah, even for earthquakes, if my choice is I can have one general purpose sensor for like wildfires, earthquakes, and lots of other things, I would deploy a network of cameras, I think.
I wonder if that's because cameras are so good and so cheap.
And so versatile, like
Yeah.
many things end up with a visual signature, right? Fires have a visual signature, vibrations have a visual signature, like almost everything that pumps out energy creates a visual signature.
This would oddly be an application where you might want a camera that has a rolling shutter, because then you could train your network to look for the shear.
So, by the way, there is something that, sorry, I wanted to talk about, but apparently I had some sound issue. But Joshua talked about weighing scales, okay? And the thing that it turns out that I have a company, okay? We are in business. We are making money out of weighing without scale using cameras. Okay, and basically what I've built there is a simple, that is more complex than I thought at the beginning, where I'm trying to mimic the human ability to measure just by looking, to weigh just by looking at someone. When you look at someone, you say, oh yeah, that person is about that much kilo or pounds, depending on where you are. You can also give us some estimate of the size. Okay? And it turns out that with a camera, so with an artificial eye and some math behind it, including machine learning, we can be pretty accurate, because our system is a 5% error rate right now and improving.
So this is an example of a sensor that would potentially be controversial to actually implement in its traditional form.
Sorry, what do you mean here? I can see where it could be controversial, but for me, it's in agriculture, so it's not about people and so on. It's about animals. Okay. So
yeah.
So of course, it could be the same technology could be used, as a complementary to face detection system, definitely. So it could be controversial in that way. Is it what you mean?
Yeah, I'm just saying, like, in terms of the societal implications of like sensors. People aren't bothered by security cameras, which are ubiquitous, but they would be bothered by sensors that would be specific to measure some of the things that we actually can measure, such as like heart rate, is the example. But
Indeed, yes. Oh, this was just an example of something I do in agriculture that works, and where we replace a traditional sensor, a typical weigh scale, by a camera. So it's really the camera eating the scales, because it turns out that in several scenarios, it works much better, actually.
So Eric, in this case, what you're using is a kind of like inference-based narrow estimation, right? Like if you know it's a cow or a sheep, then you know it's like a biological thing with density approximately close to all biological things close to water. So it's almost like it's a Bayesian measurement sensor, which is it's not directly measuring weight. It's like measuring the weight given the inference that it is in fact a cow or a particular kind of animal. And if you mess with that, the method won't work. And the example I'm thinking of is I went to a show in Vegas like a long time ago, 15, 20 years ago, and there was like a comedian juggler. And like he did things like, bowling with 3 bowling balls, and that's a heavy ball-shaped object. And then he pulled a joke on us where it looked like he brought out 3 balls, but one of them was actually a balloon. And he got a huge laugh because he was juggling it and the balloon just flew away. So you can kind of like, to the point of that is, what you sense is a function of what you think you're seeing. And this, I think, also actually connects to your abductive reasoning general theory of like, you're looking at something, you're making a first pass inference of what you're looking at. Then based on what you already know about what you think you're looking at, you can infer certain other things, right? So that's kind of like a general sensing and detection strategy here.
Yes, and
sensing with assumptions.
Yeah, like in agriculture, like
cube.
Yeah, go ahead.
Sorry, the tungsten cube or something like it has very much density and it's trending, right? Like it's very heavy or something.
Yeah, metals are a good example, like osmium all the way to like lithium. Well, lithium would burn in an atmosphere, but like all the stable ones, you would get it's like huge range in like weights. And like the more you know, the more you can detect. Like in agriculture, like I saw a video of like a machine that separates ripe and unripe tomatoes, and that's just red and green detection. But then you can get at how do you violate that assumption, like artificial ripening with acetylene, right? And that means that color becomes uncorrelated with ripeness state, and then you do actually need to squeeze it a little bit to see if it's actually ripe or if it's just changed color prematurely. So there's like lots of assumptions buried in this kind of sensing.
Yes, and so
yeah, go on.
Sorry, Venkat, you're totally right, and it's something I was cut also from the sound. Is that when Joshua, you talked about the catalyst, okay? So I think I understand what you mean by that word, but I think most of the time we talk about the proxy, okay? And this is
that's better. Yeah.
In system design, it's something when we choose what component we put in the system. Sensor choice is we have a budget when we look at the Mars rover and so on. And so, for example, for the tomato ripeness detecting devices, it's something that a couple of companies have done, because I remember one company 5 years ago, they were trying to do that with the thermal cameras, okay? But thermal cameras are expensive, okay? And so it was a tiny startup called Huxley, by the way, and they just gave up basically. But another company came with off-the-shelf sensors, just cameras, and they just use a proxy to measure. So they take standard images, but after that they do computation I don't remember the proxy they were using. And so this is something that I wanted to come to, is that thanks to Venkat actually, is that in my case of measuring the weight of animals, so in farming, yes, it's a very specific, it's a system that was tailored to do just that, okay? So if I measure something else, like the weight of a chair, it won't work, okay? So but that's not the goal of the system anyway. But the thing that is important is, sorry. The thing that is important, yes, is that earlier I said, yes, it's an example of a camera eating other sensors, okay, the weight scale. But in fact, something I wanted to say that it's not only the camera, it's a vision, and a vision system nowadays, it's a camera plus compute. Camera plus compute is eating other sensors more and more, okay? So the compute, in my case, okay, is to be able to, I take a standard image with a standard camera, and after I do extra compute where I use a proxy that I have designed to evaluate the weight. So I don't measure directly the weight. I measure a proxy of the weight to be able to replace the weight scale, basically, if that makes sense.
Assume a spherical cow and then use a optical calipers.
Yep. So in my case, the system will just not detect the sphere because a cow is not spherical. So it will just say there is no cow in that case. Okay? But it's a design choice. Okay. But you see, it's an edge case. Okay. The thing that the premise to say that a cow is spherical never hold in my data set, basically. So the system will say, I just don't know what it is. I can't measure it.
I'm curious in your system why you didn't use more direct volumetric detection that will sensors such as LiDAR, because you could just directly measure the volume of the cow.
So the reason for that is because I just found a much easier patentable technology. I mean, much easier, because the system I developed used a 3D camera, so not a LiDAR, but a 3D camera.
Right. Yeah.
Because the idea was to approximate an animal as a sphere, exactly as you said. Okay, and that works to some extent. Okay, we could get some performance from that. You know, it's a couple months experimenting, and I could get it to maybe something 20% accurate. Okay. But the thing that when we try to see how to put that in production, we found a patent. And surprisingly, the patent is from a Japanese guy here who is doing something totally unrelated. Okay. But the thing that because of that, we thought that it was just a waste of time to try to push more on that one. Okay. And it just hit me that there was a much easier way. And so the way, so I hesitate to reveal too much, but basically it's instead of using complex cameras, it's using plain standard cameras off the shelf, okay, and to structure the environment in such a way to simplify what we are looking at. Okay, so basically I'm constraining the environment. Okay, I don't put the camera in an arbitrary way. It must be in a very specific way to sense the data, so that my proxy becomes valid and my calculation becomes correct. I hope I'm not too abstract here. Okay, the thing that I never thought about revealing too much about that pending patent stuff, basically.
Yeah, I mean, there's also a lot of things you can do to kind of effectively cheat using the camera, such as using a laser line to actually triangulate the 3D volume just by a direct triangulation measurement. And this is a pretty common hack, if you will, to get a very dead reckoning accurate 3D volumetric measurement of something, especially if you can move it. One example there is wood scanners in lumber processing. In lumber processing today, it's all heavily automated, and there's very high-speed optical scanners that you run boards through, and it automatically cuts out things like knots and bad sections and these things. And that uses these very high-speed cameras. Sometimes they'll also mix in X-ray. X-ray is more common at the actual lumber mill itself, where you have a log covered in bark, which is very hard to tell what's within. So you actually do a CT scan of the entire log to optimally utilize the board foot with the CNC guided saw. X-rays are in general, I think, a superhuman sensing modality. Maybe to close it out, I think we are out of time here, but to close it out, I think some of the interesting sensors here for me are in health. The health sensors are pretty interesting, and there's a couple things that remain to be kind of like the $1 million like unsolved problem. The first one is continuous blood pressure monitoring. Or sorry, I just confounded those. Cuffless blood pressure monitoring. That's what Whoop would love to have instead of just HRV on their you know kind of like on their deck. So cuffless blood pressure monitoring, that often involves today using a heuristic where you calibrate it against a cuff-based blood pressure monitor, and then it kind of like uses some voodoo and interpolation based off of other parameters that it's measuring to try to interpolate the blood pressure. The other one is continuous blood glucose monitoring. There's been a lot more things there that have gotten pretty close. I think one of the most famous attempts was pretty heavily backed by Google attempt to put it in contact lenses. So you actually can put the detector in a contact lens, and then you can go ahead and put an antenna in that and then sync up the data pretty regularly. Those are kind of the two really, really big ones right now in consumer electronics and wearables and health. And then I would say, I think one of the most impressive sensors that we have today are MRIs. MRIs are just like, when you understand how those work, most technology is incrementally developed, like most technological progress is incremental, but an MRI is a good example of a piece of technology that was just like, wow, this was a lot had to be figured out at the same time for this to work at a minimum viable level of functionality.
What's the sensor, Jascha?
The MRI?
Yeah. The MRI. Okay.
Yeah.
Yeah.
The MRI scanner. Yeah, especially just, yeah, it's I don't know. I find it's really an incredible innovation. And the most interesting recent development in MRIs are in portable MRIs. I don't know if you guys have seen those. You've seen these? They're pretty badass. Where you use huge, really gigantic permanent magnets, like insanely large permanent magnets. And then, so this is a portable MRI machine. It has a pretty low field strength, but it actually does work. And this is kind of like the next generation of that non-invasive imaging modality in medicine. But portable MRI machines coming to urgent care near you. All right. I think that's all I've got for this evening. How was this format? Was this format interesting? Much more conversational?
Yeah,
It's pretty fun.
For topics where all of us know something, it's a refreshing change of pace from a presentation one. Yeah, I like it.
Same.
Cool.
All right.
Thank
All
you
right.
very much.
Thanks, Jascha.
Thank you.
We'll save the recording and share it when it's processed. See you guys next week, and we'll discuss on the Discord what to talk about next week, since we're still waiting for Mayor to come back from his vacation.
I think he will not join next week either, because there is another vacation, I think, in Israel.
Yep. So that's why we should think of something else to do next week. Yep.
Okay,
All right.
sorry.
See you guys.